Hello, everyone. I'm Supranta, and I'm a postdoc at the University of Arizona. Today in this talk, I'm going to talk about fast inference methods for cosmological data analysis. But before I start the talk, a couple of words about me. As I already mentioned, I'm currently a postdoc here at the University of Arizona. Before that, I was a PhD student at University of Waterloo, and I did my undergrad in India at IIT Kanpur. I'm interested in a bunch of different topics. In particular, in this talk, I'm going to talk about these fast inference methods using emulators. But other than that, I'm also interested in building Bayesian pipelines for doing field level inference. And during my PhD, I did my PhD work on using direct measurements of peculiar velocities as probes of growth of structure in the nearby universe. So if you're interested in any of these topics, I would love to talk to you. So just send me a message on Slack if you're interested to talk about any of these. So now let's get into the main talk. So I think we are currently at a very interesting time in observational cosmology. In particular, we recently had the stage 3 surveys like DES and KIDS conclude their observations, and we're on the cusp of launching these big stage 4 surveys to observe the universe. In particular, DESI has already made its first light. Other observatories like Vera Rubin Observatory and the Euclid and Simons Observatory will be launched in the next few years. Beyond which, in this decade, NASA will also launch two space-based observatories called SphereX and WFIRST. So all of these surveys will be probing our universe at an exquisite precision, and it will be probing the universe through a bunch of different cosmological probes like weak lensing and redshift space distortions, baryon acoustic oscillations, and so on. By analyzing the data from all of these different probes, we might be able to say something very interesting about the nature of fundamental physics. For example, what is the nature of dark energy? Is it a cosmological constant, or there's something beyond that? We will also probably be able to measure the total mass of neutrinos, and other surveys like SphereX are going after the primordial non-Gaussianity, which measures the amount of interaction in the very early universe. Now, going from the data to make inferences about physics is a hard process. So to demonstrate that, here I've taken, in this talk, I'll be talking mostly about these 3x2 point analysis. What I mean by 3x2 point analysis is the joint analysis of 3 2-point functions. The first is just the cosmic shear 2-point function of photometric surveys, which can be jointly analyzed with the 2-point function of galaxy-galaxy lensing, which means correlating the positions of foreground lens galaxies with shapes of background galaxies, and the third correlation function being the galaxy clustering, where you correlate the positions of these lens galaxies. And because these 3 2-point functions have different dependence on systematic parameters, say for example galaxy bias, by analyzing 3 different 2-point functions, we get much tighter constraints on cosmological parameters than analyzing any of these alone. Now, the analysis to get from the 2-point functions to cosmological contours is not an easy task, but I've tried to simplify some of the steps in the process to just demonstrate how complex it can be. And by the way, I mean, this is a huge simplification of the true process, and I don't even know some of these processes very well. One thing to remember, though, is that the data analysis of these stage 4 surveys are probably going to be systematics limited, which means we need more complex theoretical modeling of different systematic effects, and which will also necessitate using robust and better data analysis methods. In particular, in this talk, I'm going to talk only about the inference process, which basically consists of this part of the flowchart, and some of the challenges that we face when we in the inference part of these data analysis pipelines. In particular, the main bottleneck in trying to in the main challenge in the inference process is the fact that the inference methods that we use, either MCMC or nested sampling methods, are computationally very expensive. It can require, of each MCMC run for, say, LSST 3x2 point analysis, will require of the order of 10,000 CPU hours. Now, if we had to do just one such analysis, it's not a big deal. But for robust analysis, we need of the order of thousands of these simulated MCMC runs. The reason we need so many runs is the following. So when we try to determine the analysis choices and the choice of priors and scale cuts and so on, to quantify the impact of different systematic effects, we need to make a bunch of different simulated runs. So for example, these two plots are taken from a couple of papers from the DS collaborations, where they were trying to determine what is the level of what is the level of complexity in the modeling that is required to deal with different systematic effects. So for example, in trying to determine the impact of intrinsic alignment, what you can do is you can create a data vector which is contaminated with a model of systematics, and then you try to analyze with a simplified model of the systematics. And you see that where is it that it breaks down, and that determines what is the complexity of modeling that is required in the analysis. Similarly, you can determine the scales that needs to be analyzed to determine if linear galaxy bias model is correct, is going to be enough, is complex enough to deal with the data complexity. Now, doing such analysis requires hundreds of MCMC runs. Now, each of these runs, remember that each MCMC runs requires a few thousand CPU hours. So this sort of analysis gets computationally prohibitive. Another place where you might require many simulated runs is trying to come up with the optimal service strategy. LSST and WFirst and so on are going to be are surveys that are being designed with billions of dollars of investment. And so in that case, you would want to make sure that the analysis that you're doing is indeed the optimal one. So to do that, you need to make sure that, so for example, you can envision two different service strategies for LSST, where one is just wide before going deep, and the other is you go deep before you go wide. And both these choices could have different constraining powers on the cosmological parameters. So that sort of a thing requires a lot of MCMC runs, and that leads to prohibitive computational cost. So we want to now accelerate the inference process, but to do that, we have to first identify where is the computational bottleneck. So the computational bottleneck in this flowchart is simple. It's in the evaluation of the model correlation function. The model correlation function relies on using Boltzmann code and numerical integration, which are computationally expensive. And the other thing to remember is that the computation of these model correlation functions as a function of the systematics parameters and the cosmological parameters enter into the MCMC analysis at each step of the MCMC analysis. So you need of the order of 10 to the power 5 to 10 to the power 6 evaluations for each MCMC runs. So if we can speed up the evaluation of the model correlation function as a function of in the MCMC analysis, we might be able to accelerate the inference process. So one simple way to do that is by pre-calculating a number of these model correlation functions and then feeding this into an emulator, and then after training the emulator, we can just forget about the full model and then just use the emulator for faster analysis of the model data vector. Now, this is not a new idea, and this has been used in cosmology since the early 2000s for CMB data analysis. But the problem here is that for stage 4 surveys, we will need to perform our inference in fairly high dimensions. So for example, as I already said, stage 4 surveys will require more complex systematic modeling, which will lead to of the order of 50 dimensional parameter space. Now, for such high dimensional parameter space, naively sampling your training points from the prior range will not work. And to convince you of that, I have created this simple numerical experiment where I take a d-dimensional Gaussian and I create a Latin hypercube sample within -4 sigma and 4 sigma of this Gaussian. And then I take Latin hypercubes until I have 50 points within the 3 sigma volume. Now, the reason I do this is that, to do the emulation, one thing to note is that we need many points in the high posterior region, which is where we need accurate modeling of the data vector. So this number of data points that you need to get just 50 points within the high posterior region goes up exponentially. So for example, in 12 dimensions, the number of points is already of the order of 10 to the power 5. And if you go to 20 dimensions, it gets to 10 million. So what this means is that emulation in high dimension is highly non-trivial. You need some interesting way to get the data points that in the region that you care about. And the region that we actually care about is the region of a high posterior region, because like the MCMC chains will only be exploring the high posterior region. So therefore, in order to get good emulators in this region, we came up with an iterative scheme to try to get better emulation and better posteriors for cosmological data analysis. In this scheme, the way it works is that we first start off with a rough Latin hypercube sample from the prior range. Now, as I already mentioned in the earlier slide, this will not lead to a very good posterior. This will not lead to a very good emulation of the data vectors. However, what we can do is we can then use this as this rough emulator as some sort of a guide to zoom into the high posterior region, and then add the training samples by sampling from a tempered posterior using the emulator. And then once we have taken some of these points from the high posterior region, we'll add that to our training sample, and then we'll do our emulation again. We'll train our emulator again by adding more samples from the high posterior region. And by doing that a few times, we will zoom into this high posterior region, and there the emulation would be much accurate. And as you can see here, like the results lead to very, very tight constraints, very, very similar constraint to using the full model. So here in this animation, I'm showing a toy example of that by doing it on a 2D Gaussian. So here what I've done is we start the iteration 0 is where I've just drawn from the prior range and then trained our emulator so that we are sampling from the high posterior region and then adding that onto the training sample until there's more and more points in the high density region. So doing so can lead to not only accurate emulation, but also leads to a lot of speed up. So here I'm showing the contours of a very realistic 3x2 point forecast for LSST year 1 like survey. Here I'm showing here in this posterior, I've only shown the likelihood dominated posterior, but there are many other parameters that I'm not showing here. And you can see that you cannot basically distinguish between the contours that you get from the emulator and from the full model, which is based on this code called COCOA, which uses Cobaya and Cosmology in its analysis. And this is a very realistic analysis, by the way. I mean, you can almost take the code as it is and probably do a data analysis as it is with minor tweaks. There's realistic systematics modeling. We are doing the analysis in real space as opposed to harmonic space, which requires some work, and this has already been done. Now, while this leads to almost an order of magnitude speed up in the inference. Now, while this is already impressive, the main gain that comes from using this emulator is if we can reuse the emulator. In order to showcase that, what we do is we do an analysis of what is the impact of baryonic effects that will have on 3x2 point analysis of LSST. So baryons, like our universe, not only consists of dark matter, but also consists of baryonic matter. And what that does is, due to physical processes, that leads to a change in the power spectrum on small scales. And usually in weak lensing data analysis, the way this is mitigated is by only analyzing the large scale correlation functions. And if you do that, one thing you have to do is you need to determine what scale cuts you want to use in your analysis. And to do that, you need to run a bunch of different simulated analysis. Now, in our case, once we have trained our emulator, we can just reuse our emulator and impose different scale cuts with the emulator. Now, while the full process of the iterative training and sampling takes quite long, rerunning the emulator is actually very fast. And this is shown here, where all of these 3 runs are based on 3 different mitigation schemes. And as you can see, if you do not account for baryons at all, that can lead to highly biased results in your cosmological parameters. So to account for these, we looked at 3 different mitigation schemes, each using the exact same emulator. And each of these runs only take about 5 minutes, which is of the order of 1,000 faster than this. Not only that, we can now just impose different scale cuts and run a lot of these analysis with different scale cuts. Here I have run of the order of 50 different runs, which would be impossible using the traditional analysis. But with the emulator, this can be done in just 5 minutes of wall time, which is of the order of 1,000 times speed up of the code. So now we can start using this for a lot of different applications, like using this to determine the impact of different systematics and optimizing the service strategies. And that is a work that is in progress, and hopefully I'll get to talk about it at some future time. But here's the summary of the talk. So I have introduced a new iterative scheme that can lead to fast and accurate inference for realistic cosmological analysis. We have demonstrated this on LSST Year 1 like 3x 2-point forecast, but you can use it for anything where the evaluation of the likelihood is expensive. And as I've already alluded to, it is ideal for trying to quantify the impact of different systematics, optimizing the service strategy, and assessing tensions in your data, and so on. Hope you enjoyed the talk, and if you have any other questions, looking forward to interact more on it later. Thank you.